Okay, welcome to this dynamic session of the ICM 2022 on the 9th of July. It's a great pleasure for me to welcome you all here. My name is Anish Koch, and I'm a mathematician at the Tata Institute in Mumbai. Today we have with us Professor Peter Varju from the University of Cambridge. So Peter is a leading expert in harmonic analysis and archonic theory, and he has won many recognitions for his beautiful work, including an EMS prize and a Whitehead prize. So it's really a great pleasure for us to be able to listen to Peter today. So without further ado, I will now introduce the talk. So Professor Peter Varju will tell us about self-similar sets and measures on the line. Peter, please.
Thank you, Anish, for the introduction. And before I begin, I would also like to thank everyone who was involved in organizing this Congress. And I know that it was a very short time and very challenging circumstances. And this is certainly a great pleasure and honor for me to give this talk. I will talk about self-similar sets and self-similar measures. So I will begin with the definition. Okay, so first, an iterated function system is a finite collection of contractive similarities on RD. So it's scaling and rotation followed by translation. That's a similarity. And so if you have an iterated function system, denoted by phi1 up to phi m the maps, then there is a unique compact set K such that it is precisely the union of the images of the set under these maps. So K is equal to phi1 K union etc. phi m K. Now that set is called the attractor of the iterated function system. Or if you don't want to refer to the IFS, then we call it a self-similar set. So the systematic study of these objects was initiated by Hutchinson in 1981. So it's a relatively young subject, only 1 year older than me. But many examples go back, in fact, much longer. So let's see some examples like that. So the first one is the middle third Cantor set. And so as you can see, this part of it is shrink copy of the whole thing. And also this other part is a shrink copy of the whole thing. So, and the whole set can be realized as a union of these two shrink copies. Then there is also the Sierpiński triangle, which can be realized as three shrink copies of itself, as you can see in this animation. And then finally, there is the von Koch curve, which is the union of four shrink copies, and now we also have some rotations by 60 degrees. So I'm waiting for the last copy. Yeah, there it is. Okay, so these are self-similar sets, and we can also put a measure on these sets to have more structure. So to do this, we, in addition to having the IFS, we also need a probability vector, P1 up to Pm. And if you have such a data, then there is a unique probability measure on RD, such that the following property holds, that if you take your measure and you look at the push forward with each of the maps in the iterated function system, and you average them, the measures that you get this way, using the probability weights P1 up to Pm, then you get back the original measure. So a measure with this property is called self-similar. So my notation, this phi of mu is the push forward of the measure, which is formally can be defined as the measure composed by the inverse of the transformation. Okay, so some first comments. The first one is that if you take the support of the self-similar measure, then you get the attractor of the IFS. Well, at least if you choose some sensible weights that all of the probability weights are positive. Yes, by the way, one thing that I wanted to say at the beginning, but I forgot, is that I'm online on Discord and I'm watching the dynamics channel. So if anyone has any questions, feel free to type it in and I will try to answer. Okay, so one reason for studying self-similar measures is because by studying them, we can also learn about about self-similar sets. So there is this obvious connection that the support of the measure is the set. And later on, I will say a little bit more about this connection. So another way of defining self-similar measures, if you like Markov chains, is that the self-similar measure is the unique stationary measure of a Markov chain, where the transitions are the maps that you have in the IFS, and the transition probabilities are the probability weights P1 up to Pm. Now there is a very nice class of iterated function system for which it's very easy to write down what the self-similar measure is. These are homogeneous iterated function systems, which means that the contraction factor, this factor lambda, is the same for each map. So if you have such an iterated function system, then the self-similar measure can be realized as the distribution of a random variable, which is a power series with random coefficients. These t sub psi j are random. More precisely, the psi j is random. It's an independent random sequence of indices chosen with probabilities P1 up to Pm. And so you multiply these coefficients with lambda to the n and sum them up. Because lambda is less than 1, this surely converges. So you get a random variable, and the distribution of this will be the self-similar measure. This is easy to check from the definition. And there is a further example, which are called Bernoulli convolutions. These appeared in the work of Jessen and Wintner in 1935 for the first time. And so here are they. So this is a family of self-similar measures. There is one for each value of the parameter lambda between 0 and 1. So you just take a random sum of lambda to the n's with random signs. So the plus and the minus are random, and they are independent, taking each value with the same probability. So this defines a random variable. It has some distribution, and that's the measure that I'm interested in. So here is a histogram for a specific value of lambda. It is this 0.676. There is nothing special about this number. I chose this just to have a nice picture. So what you see on this, this is meant to be a histogram. So the Bernoulli convolution is always supported on some interval. You can compute it very easily what it is. And what I did was that I subdivided this interval into 4,000 equal pieces, very little small subinterval. And I computed how much the measure of each of those intervals, and then normalized it so that it has average 1. the whole interval, and this is what I plotted. And yeah, so we actually don't know if this measure is absolutely continuous, but if it is, then the graph that you see here is some approximation of its density. Okay, so in the next slide, so on this one, you see demonstrated the self-similarity property. So the light blue and the magenta graphs are shrink copies of the big graph, and you see that on the two sides they match the original graph, and in the middle, if you sum the light blue and the magenta, then you get back the original graph. So this was to illustrate the definition of self-similar measures. And so on this animation, you can have an idea about how these objects look like. So you see the histogram for changing value of lambda from 0.5 to 0.8. So basically, broadly, what you can see in this animation is that it starts out something very oscillatory, and then as lambda gets closer to 1, it starts to behave smoother and smoother, and when lambda is very close to 1, it really looks like a Gaussian, which is I guess the point where the central limit theorem really kicks in. But if you pay a little bit closer attention, then you can see that this smoothing is not monotone. So there will be some values of lambda where suddenly this graph becomes a bit more oscillatory. And so actually, our current state of knowledge is that these measures are absolutely continuous for almost all values of lambda between 1/2 and 1. But we don't actually know precisely what the exceptional values are where it is not absolutely continuous. We know some such values. And if you look at those lambdas where this graph becomes suddenly a bit more spiky than it is in the neighboring lambdas, then it turns out that you are actually close to one of those parameters for which we know that it's singular. These are called Piso numbers. Okay, so I hope I managed to convince you that these are very rich and structured objects and very curious, because I will now talk about them. So what are the questions that you would like to understand? So, well, if you see a fractal, probably the first question that you want to answer is what the dimension is. So that's a big question. What is the dimension of a self-similar set or a self-similar measure? In a minute, I will make it more precise what I mean by dimension. Then another question that I briefly mentioned during the animation is the question of absolute continuity. So when is it true that you have a density with respect to the Lebesgue measure? Then Fourier decay is also a very interesting question, which is very far from understood. And then there were also a lot of recent work on metric Diophantine approximation, which is very exciting. So in this talk, I will talk only about dimension. But if you look at my article in the proceedings, which I believe hasn't yet appeared, but nevertheless you can find it on arXiv, then there is a short survey about absolute continuity and Fourier decay. Okay, so let me tell you about what I mean by dimension. So first, in the case of sets, this can either mean the Hausdorff dimension or Minkowski, or in other name, box counting dimension. So in general, these need not be the same for, there are sets for which these two notions of dimension are different. In fact, Minkowski is not even defined always. But it turns out that self-similar sets are sufficiently nice, and these two values of dimensions coincide for them. This is a result of Falconer from '89. So this means that I don't have to specify which one I mean. Okay, so what could be the dimension? I will speculate a little bit, and I begin by briefly recalling what the Minkowski dimension is. So what you do is that you count the number of R balls that are necessary to cover the set. An R ball is just a ball of radius R. And then you look at which exponent you need to raise R to get this number. And if you are lucky enough, then as you take R to 0, these exponents will converge, and this is the dimension. And as I said, for self-similar sets, this limit exists. Okay, so now suppose that you have a homogeneous iterative function system for simplicity with M maps and with a common contraction factor lambda. Suppose that your self-similar set K is contained in a ball of radius capital R, which I denote by B. Then one thing that you can do is that you can just take, you can compose your maps. You can take all n-fold compositions of these maps and look at the image of this ball B, which covered the original set K. And now the union of these, because of the self-similarity property, will cover K again. So you get a covering with m to the n many balls, which have radius capital R times lambda to the n. And if you plug it into this formula, then what you can conclude from this is that the dimension is not bigger than log m over log lambda inverse. So this observation motivates the definition of the so-called similarity dimension. This is really a number attached to an iterated function system, and it is defined as log m divided by log lambda inverse. Okay, so the first observation is basically what we have already made, is that the dimension of the self-similar set is always at most the similarity dimension of the iterated function system. Something which is a little bit less trivial is that if you have a very nice separation condition for your iterated function system, namely that the images of your set are pairwise disjoint. If you look at the images through the maps in the iterated function system, or actually the right condition is something called the open set condition, which is a slight weakening of this. Then it is actually true that the dimension of the self-similar measure is the similarity dimension. So this first naive guess is the right answer. So I don't want to give the definition of the open set condition to save time. I just want to give you a little bit of intuition. So if you remember back, the first example that we have seen was the Cantor set. And so in that case, the image of the Cantor set with respect to the two elements in the iterated function system were disjoint. You had these two separate copies. If you think back about the other two examples, so say the Sierpiński triangles, then if those three smaller triangles, which are the images of the original set, they actually touch each other. So it's not quite true that the images are pairwise disjoint, but they are almost disjoint. The intersection is very small. And in such a scenario, the open set condition can still hold. And in fact, all of the three examples fall under this line. Okay, so from now on, I will just talk about self-similar sets on the line, as it was advertised in my title. So the dimension is d is equal to 1. And now I ask the question is that maybe can it be true that this naive first guess for the dimension, which is the similarity dimension, may hold more generally, not just not just when the open set condition holds. Now, if you think about this, then you will realize that there are two rather obvious obstructions why this may fail. So the first one is that the dimension of the self-similar set will never exceed the dimension of the ambient space, which is 1. On the other hand, you can make the similarity dimension as big as you want. So if you look back at the definition, it is defined as log m over log lambda inverse. And really, there is nothing that would stop me from putting as many maps in my iterated function system as I want. So I can make this the similarity dimension as big as I want. It can be bigger than 1, and then in that case, it will surely not equal the dimension of k. The other obstruction is that that it could happen that I can realize the same self-similar set as the attractor of different iterated function systems. So the similarity dimension is really depending on the iterated function system. So if I change the iterated function system without changing the set, then probably the similarity dimension will not be the right answer for each choice. And indeed, there is a silly thing that I could do. I could include in my iterated function system the same map several times. So if I do that, then I will artificially increase the value of m, and without changing the self-similar set itself. So this is one thing that we would need to exclude. And in fact, we need to elaborate on this point a little bit. I say that my iterated function system contains no exact overlaps if the following holds, that when I look at all the composition of k different maps, or you can, they don't have to be different, you can take the same map several times in this composition if you want. So this way you can create m to the k maps, and if they are all different for all values of k, then I say that my iterated function system contains no exact overlaps. So and this is again something that I would want if I'm hoping that the similarity dimension will be the answer to my question. And there is a conjecture by Shimon which predicts that these are the only two obstructions. And so what it says is that if you have an iterated function system that contains no exact overlaps, then the dimension of the self-similar set will be equal to the minimum of the similarity dimension and 1. Okay, so I also want to talk about the dimension of measures. So what do I mean by the dimension of a measure? So one thing that you can do is that you can look at the measure of an interval x minus r to x plus r. And you can look at which power you need to raise r to get this measure. And you hope that when you take the limit r goes to 0, then you converge to something. And if it converges for almost every choice of x, and moreover, the limit doesn't depend on which points you take, then we say that, that the measure is exact dimensional. And if it is exact dimensional, then we call this this limit its dimension. So this is the notion of dimension that I'm going to use. So this doesn't exist for all measures, but if it exists, and if you have an exact dimensional measure supported on a compact set, then the dimension of your compact set will be at least as big as the dimension of the measure. Now, this fact is actually true in. This is a very weak form of a much stronger phenomenon, but for the purposes of my talk, this will be enough for us. So this is very nice, and the reason why this is very nice is because usually it's easy to estimate the dimension of a set from above, because to do that, the only thing that you need to do is to construct some covering of your set. And when you have a covering of your set, then you can plug it into your definition of, say, Minkowski dimension or Hausdorff dimension, and that will give you an upper bound on the dimension of the set. But giving lower bounds on the dimension of a set is much more tricky. And what this tells you is that if you can find a measure on your set and you can compute the dimension of that measure, then this will give you a lower bound. So this is very useful. And here is another good news, and is that self-similar measures are always exact dimensional. This was proven by Feng and Hu in 2009. So it makes sense to talk about the dimension of self-similar measures in the sense that I described. And then there is also a notion of similarity dimension for a homogeneous iterated function system. And so this and the probability vector P. So this is the purpose of this definition is to have a guess for the dimension of the self-similar measure. And this is defined as the ratio of the Shannon entropy of your probability weights over the logarithm of the common contraction factor to the -1. So if you don't know what Shannon entropy is, then just consider the uniform probability distribution. So where each p is equal to 1 over m, and then you get log m over log lambda inverse, so the same as the similarity dimension of the iterated function system without weights. Now, the conjecture about sets has a counterpart about conjecture, a conjecture about measures. And this also predicts that if you have iterated functions without exact overlaps, then the dimension of the self-similar measure will be equal to the minimum of the similarity dimension of the iterated function system with the weights, or 1, whichever is smaller. So everything that I talked about so far can be extended to inhomogeneous iterated function systems, but to save time, I will not talk about it, and you can see it in my proceedings article or in many other places. And so now I want to tell you about what we know about these conjectures. And before I do that, I need to introduce another notion. It is another separation condition. So let's consider an iterated function system. For simplicity, I assume it's homogeneous. And for each positive integer n, I define the level n separation as follows. I take all n-fold compositions of my maps, and I look at the image of 0. And so actually this is nothing else but the translation component of your similarity, which is the n-fold convolution of your maps. And I look at all the differences between these points that I can get, and I take the minimal distance. That's the level n separation. So not having exact overlaps is equivalent to this number being strictly positive for all values of n. So there is something called the exponential separation condition, which says that it is much stronger than not having exact overlaps, because you not only require that the n level and separation is positive, but you want it to be bigger than something specific, and that's some constant to the n, where this constant can be arbitrarily small. So this is stronger than not having exact overlaps, but actually it is a very weak condition. It holds typically. So this is in contrast with the open set condition that I mentioned before. That's something that is really special. It holds in special situations. This is the opposite. This usually holds, and if it fails, then it really fails in special situations. But it is not straightforward to test this condition. So if I give you an iterated function system, you might not be able to decide whether this holds or not. So the first result was proved by Hochmann, and so actually he gave a talk at the Congress 4 years ago where he talked about this. But it is a very important result, so I mention it. So it says that the conjecture holds, the conjecture about self-similar measures holds if the exponential separation condition holds for the iterated function system. And actually, with the right generalization, so you need to modify the definition of level n separation in the inhomogeneous case, but this actually also works in the inhomogeneous situation. And then it also implies the conjecture about sets under the exponential separation condition. So as I said, it's if I give you a system, you might not be able to test whether the exponential separation condition holds or not. But there is a nice class of nice situation when it is easy to verify it, and that's when all of the parameters that you have in your systems are algebraic numbers. So if all of the contraction parameters and all of the translation parameters in your maps are algebraic numbers, then this condition holds. And then by Hochmann's theorem, the conjecture also holds. So this has been extended very recently by Rappaport, who proved that actually it is enough to assume that the contraction parameters are algebraic and the translation parameters can be whatever you want them to be. But this doesn't follow from the first theorem of Hochmann, so at least not in an immediate way. So this iterated function system, is family of iterated function system, contains there are members in this family where the exponential separation condition actually fails. The next result is about homogeneous iterated function systems of two maps. So if you have only two maps in your system and they have the same contraction factor, then the conjecture holds without anything further to assume. And actually, this is equivalent to asking the conjecture for Bernoulli convolutions. So these are those measures whose histograms I showed you before. So if you want so the case when the contraction is algebraic, that was covered by Hoffman, and I proved the transcendental case recently. And then together with Rappaport, we tried to extend this proof to iterated function systems of 3 maps, again homogeneous. And we succeeded if lambda is sufficiently close to 1, so if it is larger than 2 to the minus 2/3. And we also have a conditional result. And to explain what the conditional result is, I need to tell you about some other things. So the first one is the notion of Mahler measure. This is a quantity assigned to algebraic numbers. So if you have an algebraic number lambda and it has a minimal polynomial in this form, AD times x minus lambda 1 times etc. x minus lambda d. So AD is the leading coefficient, and lambda 1 up to lambda d are the Galois conjugates of lambda. Then the Mahler measure is defined as the product of the absolute value of the leading coefficient multiplied together the absolute values of those Galois conjugates which are outside the unit disk. Okay, so if you have never seen this before, then basically what I wanted to say is that if you just take a rational number, then the Mahler measure will be the maximum of the numerator and the denominator. And the reason why this quantity is relevant to this problem is because this is a quantity that appears in Diophantine approximation. So if the Mahler measure is small, it means that you can use it to show that there are no other similar numbers very close nearby. And this will be important later if I manage to get to it. Okay, so one of the ingredients in the proof of the case of 2 maps is this result that I proved with Breuer. With Emmanuel Breuer, it says that if you consider the iterated function system of 2 maps, so x maps to lambda x or lambda x plus 1, and if this iterated function system has lots of exact overlaps, then the Mahler measure of lambda can be bounded by some constant which depends on this lots of what this lots of means. So this has to be quantified in the right way, which I don't have time to talk about, but you can see it in my proceedings article. So this is one of the crucial ingredients in the proof of the conjecture for 2 maps. And this was the bit of the proof that we couldn't generalize to 3 maps with Ariel. So what we managed to prove is that if a suitable analog of this theorem holds for the iterated function system of 3 maps, where you map x to lambda x or lambda x plus 1 or lambda x plus t, then the conjecture also holds for these iterated function systems. Again, I don't have time to properly formulate this hypothesis, but I hope you get some idea. And if you are interested in the details, you can see them in the proceedings. Okay, so finally, I wanted to tell you a little bit about the proofs, and in particular, I want to point out what the difference between 2 maps and 3 maps is. So let's recall what was the definition of the level and separation. So you take all n-fold iterations of your maps, and you look at the image of 0, and you look at the minimal distance between these points that you get. So if you take the iterated function system with 2 maps, then you can work out what this definition is. And so this thing that whose minimum you are taking will be equal to a polynomial evaluated at lambda. Lambda is the parameter that parameterizes the iterated function system. And you need to run this minimum for over all polynomials of degree n whose coefficients are in the set -1, 0, and 1. So now what this means is that if you have some delta n which is very, very small, then what that means is that p of lambda has to be very small for such a polynomial. And it turns out that this also means that lambda itself has to be very close to a root of such a polynomial. Now, what is very nice is that these roots repel each other, and by which what I mean is that you can estimate how close they can be to each other. And so if you are really, really close to one of these zeros, then there will be no other zero close to your lambda for a while, even if you are increasing the value of n. And so what this means is that that the original zero that you initially found will be still responsible for how small delta m is in a range above n. And so if you can do this for sufficiently long enough, then at some point when m will be sufficiently big, then you will no longer consider this smallness to be so small. So what I mean precisely is that using this argument, you can prove the following: that if you don't have exact overlaps, so it just means that delta n is positive for all values of n, then there are infinitely many values of n for which you have a bound of this shape, that delta n is larger than n to the minus cn. Now, this is just a little bit weaker than exponential separation. So what you would really like to have here is just exponential in minus cn. And if you had that, then you would be done just by the result of Hochmann. And this actually might be true, but we have no idea how to improve on this. Nevertheless, this is already very nice. And actually, if you have this bound for sufficiently many values of n, which are not too far from each other, then this is already enough to prove the conjecture. So this was another ingredient in the proof of the two maps case, which was done by Emmanuel and me. So actually, these dates that you see here do not reflect the true chronological order. So these papers were all were written before my 2018 paper, where I proved the conjecture for two maps. It's just that they appeared later. Okay, so so now what can be done is that if a relaxed version of this constraint fails for a sufficiently long range of n's, then you can actually improve on your bound, and you can show exponential separation for some larger value of m. So I don't have time to tell you what I mean by relaxed, but basically the point is that what I wanted to say is that either you can verify the condition required for my theorem with Emmanuel, or you can verify the exponential separation condition, and you are done by the work of Hochmann. So I'm really out of time, so I just want to tell you the punchline. So what is the difference with three maps is that so previously you had that the delta n vanished along a single point, and this had some distance between, you had some distances between these points, and this was crucially used. here in this case, you have vanishing along curves in the lambda t plane, and these curves will intersect each other, and they don't have distances. And this will make the argument just totally break down. And in fact, what can happen is that the delta n may decrease arbitrarily fast in the case of three maps. Such examples were actually given by Baker and then Barany and Kanmaki and then others. So in this case, you need to work harder because you don't have this these nice bounds that are available in the two maps case. And I'm already over time, so I just thank you for your attention.
Thank you very much, Peter, for this excellent talk and for telling us about your wonderful results. So I can't see anything on Discord. Maybe I can ask a quick question, if you permit. So what about more than three maps? Are there any thoughts about conjectures, what might happen?
So the conjecture is still expected to hold. Basically, there are two issues. So one is that so that even in the three map case, there was this condition that we just don't know how to do for three maps, and for more maps it's probably more difficult. And then there are some other issues. So we try to do more maps, but somehow got stuck. But I think that probably it's worthwhile trying to push it further. So the issue is somehow that you need to do some limiting arguments, and if you have three maps, then you have some kind of singularities that you need to deal with, and if you have four maps, then the singularities are much worse, and we just what we did just didn't work. But maybe it can be pushed. What I think is more difficult is this condition that we couldn't do even in the case of three maps that possibly requires something drastically new.
Okay, great, thanks. And also just a kind of open-ended question. So is there anything in this line in higher dimensions?
Oh yes. Hoffman generalized his results to higher dimension. And so under the exponential separation condition, you can do very nice things. If you don't have exponential separation condition, then as far as I know, we don't have anything yet.
I see. Okay, great. So thank you once again for this beautiful talk. And
thank you. So I just wanted to say that I will be on Discord for a little while. So if someone has questions, feel free to ask there.
Thank you very much.
Thank you.